Okay, welcome back everyone to GOCC. Today we'll be hearing from Elia Mazzucchelli on from the Amplituhedra to exterior cyclic polytopes. Before we get started, let's just recall our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that, Elia, whenever you're ready.
Very nice, very nice. Thank you, and thanks for this invitation. I'm happy to share, I think, some intriguing combinatorics of these mysterious objects, which are the Amplituhedra. And this is a joint work with Lizzie. So here she is. And this is from our paper Convexity of Amplituhedra and the Exterior Cyclic Polytopes, which you can find, for example, on the archive. So this is the outline. I'm gonna give the motivation for doing what we did, and then I'm gonna tell you what amplituhedra are. Then I'm gonna mention this notion of convexity that we came across for semialgebraic sets in real projective varieties that we then used to study amplituhedra. And this then led us naturally to this polytope, which we call the exterior cyclic polytope. So then I'm going to focus a bit on this other object and on its combinatorics. And in the end, I'm going to mention something about duality. And please stop me at any time for any questions. So the motivation comes from physics, and in particular from scattering amplitudes. So I think we are interested in physics. I hope you can see my cursor. Is the description of the scattering of particles. So here is schematically represented by these incoming arrows. So we have n of them. These are very bad looking n. We have n incoming particles, and then they interact. So some things happen, and we want to the only thing, according to the rules of quantum mechanics, that we can say about this process is the probability to observe a certain configuration of momenta. So what are these momenta? These PIs are encoding the kinematics of the particle. So these are four vectors in a real four-dimensional vector space of signature 1, 3. And these vectors encode both the energy and the momentum of each particle. And then the object we are interested in is a function whose input are these n momenta. And this function is complex valued. But out of it, we can construct a probability distribution by taking the modulus squared. And this is in the end what we use to compare with experiments. So we repeat million of times certain scattering processes, and we compare with the probabilities we can compute from quantum field theory, which are an outcome of this of the computation of this scattering amplitude of this function an, where n is the number of particles we scatter. So now I want to connect directly with this more recent trend of positive geometries. So they arose for the first time in physics in the following way. So usually to compute the scattering amplitudes, so here is an example A6. So this would be the scattering of 6 particles in a specific theory. Physicists know how to compute these amplitudes, and the standard way for doing this is through so-called Feynman diagrams. So morally, Feynman diagrams represent the history that the particle could have undergone in this previous blob. Just go quickly back in this blob here. So you fill the blob in all the possible ways allowed by your theory, and you end up with by summing over all possible histories, because quantum mechanics is not a deterministic theory, and you somehow have to consider all the possibilities in one. And this is roughly the idea of Feynman diagram. So you sum over the Feynman diagrams. To each diagram, you associate a function itself, and in the end, the sum yields the actual amplitude. So this is an example for the scattering of six particles in this fancy theory called N equal 4 super Young-Mills theory, a very symmetric cousin of a more physical theory that is related to reality. So in this theory, this amplitude can be expressed as a sum over 220 of these Feynman diagrams. But here is the magic of positive geometries, is that they provide a completely different description of this amplitude, very geometric in spirit, where you forget about these Feynman diagrams, and what you're interested in is a geometric object, which I'm going to introduce now as the amplituhedron for this theory. And the amplitude is associated to some invariant function associated to this amplituhedron, which is actually differential form. And we call it the canonical form in the context of positive geometry. So the amplitude now in N equal 4 super Young-Mills becomes the canonical form of the amplituhedron. So what is the amplituhedron? Here is a definition. So you start from K plus M by N matrix. So here I fix some non-negative integers n, k, and m, such that n is greater or equal than k plus m. Then I take a positive matrix, that means with all positive maximal minors, real. And I use this matrix to define a map between Grassmannians. As you can see, I'm going to denote it by wedge kz. It's going to become a bit clear later why I denote it in this way. But anyway, it's given like this. So it maps between the Grassmannian GRKN to GRK, comma, K plus M. So it's a rational map. If you take a matrix representative for a point in GRKN, its image under this map is given by the representative of the matrix multiplied by Z transposed. So quick check on the dimensionality, then this map could make sense, is rational, because if the subspace spanned by the columns of this matrix has some intersection with the kernel of Z, then this may drop in dimension. So there is some locus in GRKN where this map is not defined. But the interesting thing is that if you restrict this map on the positive Grassmannian or on the non-negative Grassmannian, which I'm going to denote that like this. So this is the subset of the Grassmannian where all the Plücker coordinates are non-negative. If you restrict this map on this non-negative Grassmannian, then it is well defined, and its image is a semialgebraic set in GRK, comma K plus M, and this is precisely the amplituhedron. So this is a bit complicated. So this object depends on K, M, and N, three parameters, and the matrix Z I chose. But so it is pretty complicated, but the idea is that it generalizes objects which we are more familiar with. In particular, there are two extreme cases for these parameters. There is the extreme case K equals 1, where if we go back, if you put K equals 1 here, you really have a map between projective spaces, between Pn minus 1 and Pm. And this is the projection of a simplex by a positive matrix, and this is precisely the one of the realizations of a cyclic polytope. So for K equals 1, the amplituhedron is nothing else than a cyclic polytope on n vertices in Pm. The other extreme case is when K plus M is equal to N. And in this case, the amplituhedron, so I could take Z to be really the identity, and I would simply have a copy of the non-negative Grassmannian. So in this other extremal case, the amplituhedron is the positive Grassmannian, or it is isomorphic to it. So these are extreme cases, but in between, they are pretty mysterious objects. Many people have studied this amplituhedra in the last 10 years. And let me stress again the magic in relation to physics. This was a bit more than 10 years ago by Imar Kanyamed and Jaroslav Trinka, is that the scattering amplitudes in the specific theory, n equal 4 super Young-Mills, are encoded by the geometry of the amplituhedron. In particular, the amplitude, which now, because of the theory we're considering, depends on an extra parameter k, which has a physical meaning of the helicity of particles. But anyway, this amplitude that depends on k and n is encoded by a logarithmic form on the Grassmannian, which is associated with this amplituhedron for the specific parameter m equals 4. So this is related somehow to the space-time dimension, which I mentioned at the beginning. These are four vectors encoding the momenta somehow correspond to this m equals 4. So this is the physics motivation and the definition of the amplituhedron. And why is it interesting other than bypassing this idea of Feynman diagrams and giving a new perspective on amplitudes? It exposes some new properties of amplitudes that have been observed more recently. So the idea already slightly before the introduction of the amplituhedron, and I think this is actually one of the papers that motivated the discovery, or that allowed the discovery of the amplituhedron. So one of the discovery by Hodges is that the amplitude in this n equal 4 super Young-Mills for k equals 1 is nothing else than the volume of a polytope. And this polytope is the dual, the convex dual of the amplituhedron. And if you remember, for k equals 1, the amplituhedron is precisely a cyclic polytope. So in this case, we are just taking the convex dual of the cyclic polytope. And in some sense, you can associate to this polytope a volume function, which is a rational function, and this computes precisely the amplitude. And why is this nice? Well, as a first approximation, volumes are positive numbers. A volume of a polytope should always produce a positive number. So this would mean that amplitudes are positive, which is already, in principle, a surprising fact because the amplitude itself is a complex function. So it is real valued and positive on a certain region is surprising. And recently, this year, by Johannes Henn and Prashant Raman, two people in the group I'm working with, found out that actually a much stronger property than positivity holds for many amplitudes and other objects in physics, and this property is called complete monotonicity. And then with Prashant and me looked at the relation between this property and positive geometries. So this is just another step for the motivation of looking at this new perspective of amplitudes, this new description of amplitudes for exhibiting strong positivity properties. And the fact that here on this side we have the dual of the exterior cyclic polytopes is what motivated our project with Lizzie. So we really wanted to find some extension of this duality for the amplituhedron, but for higher Ks, where the amplituhedron is not just a polytope. And in order to do that, we went through the notion of convexity first. So here I'm giving you a notion of convexity for semialgebraic sets in real projective varieties, embedded already in a specific way in projective space. And it goes as follows. So you take a real projective variety embedded in Pn, and you take a semialgebraic set in it. Then you define the convex hull of the semialgebraic set in a very naive way. So what you do is you consider this set as a set in projective space. You can take the convex hull of it in the projective space. So this is a well-defined notion. I omitted an assumption that A's should be connected and there should exist a hyperplane not intersecting it. So there are some small technical assumptions which are not too strict. you can take the convex hull of the semialgebraic set in projective space, and then you can intersect back with the variety it lives in. And we are going to call this the convex hull of A and X. And then we say that A is extendably convex if the convex hull in this sense is equal to itself. So this is a very naive thing to do in principle. Here I added a remark. One can check pretty easily that a semialgebraic set in X, in the setting above, is extendably convex if and only if not only it is equal to the intersection of X with its convex hull, but with any convex set in the ambient space. If there exists any convex set in the ambient projective space whose intersection with X yields A, then A is going to be extendably convex. So here I have just a quick picture. Well, as a first remark, if we take the projective variety to be the projective space itself, of course, this is the usual notion. But what we're really interested in the end is to consider semialgebraic sets in the Grassmannian. So we want to study this notion for the amplituhedron. But here is another example. So consider X given by the vanishing locus of this quartic. So this is this blue curve here in an affine chart. And then I'm considering the semialgebraic set A here given by this orange interval on it. Opa. This orange interval here on the left. And so what is the convex hull of A in X? Well, I take the convex hull of this in the projective space. So I can do this in an affine chart as soon as I'm in an affine chart that contains the whole semialgebraic set. And this gives me this yellow shaded region. And then I intersect it back with X. And I get again A in this case. So in this case, you would say that A is extendably convex. On the right, however, you can see that the interval now is bigger. If I take its convex hull in the affine chart, is going to intersect X also in a new part. And so we are not calling this an extendably convex semialgebraic set in X. Now, why this naive notion may be better than others for studying Grassmannian and Amplituhedra? Well, at the beginning, we thought, why not consider geodesic convexity, for example? But even the non-negative Grassmannian turns out not to be geodesically convex. And one of the least requirements we had is really that the non-negative Grassmannian should be sort of the analogous to the simplex in our case, and it should definitely be convex to whatever notion we choose. On the other hand, by definition, the non-negative Grassmannian is the intersection of the Grassmannian with the non-negative, with the standard simplex in projective space, where all the coordinates with respect to the standard basis are non-negative. So it is, by definition, it is extendably convex. It is given by the intersection of the Grassmannian with the simplex. And then we thought about looking at this notion for more general amplituhedra. And this then led us to study these polytopes. So the idea is the following. So if you look at this diagram here, in the row below, we had the amplituhedron map as a projection between, or as a rational map between two Grassmannians, where we can lift this map to the Plücker embedding. Well, it's really given by the exterior product of the linear map induced by Z. So now it becomes a linear map. Well, actually, it should be rational on the projective space. Sorry about that. But you can lift this map to a rational map at the level of the Plücker embedding, and this diagram commutes. It's a very natural thing to do. And then instead of looking at the projection of the non-negative Grassmannian in the Grassmannian, we look at the projection of the non-negative simplex in projective space. And this is what we call the exterior cyclic polytope. So the exterior cyclic polytope, which again depends on three parameters k, m, n, and z, is given by the image of the non-negative simplex under this wedge KZ map. And this is a polytope. In P, k plus m choose k minus 1, which is the Plücker embedding space of grk comma k plus m. Now, again, these polytopes, so a bit how amplituhedra for certain parameters are familiar objects. Also, these polytopes for certain parameters are familiar objects. In particular, for the usual k equals 1, the exterior cyclic polytope is nothing else than the cyclic polytope, which is also the amplituhedron. So in this case, all these notions collide, and they produce the cyclic polytope. And here instead, I drew a different example for k equals 2, m equals 1, and n equals 4. So n equals 4 is, it means that I'm going to take a 3 by 4 matrix Z, and the ZI's here denote the 4 columns of Z. K equals 2 means that I have to look at the second exterior power of my columns. So these are points in this in the Plücker embedding, of GR23, which is P2 star. So this is up to identification. I'm drawing things in a plane. So these fat black dots are the images under this wedge 2Z map of the vertices of the simplex. And the exterior cyclic polytope is the convex hull of those points. So you can see if you take the convex hull, you get this lightly blue shaded region. And this is the exterior cyclic polytope for k equals 2, m equals 1, and then equals 4. It's a triangle. So how does this polytope relates to the amplituhedron? Well, the first observation is that the convex hull of the amplituhedron, but now the convex hull in the Plücker embedding. So I consider the amplituhedron in Grassmannian, but I take its convex hull in the ambient projective space, then this is exactly the exterior cyclic polytope. Now our question was, when is the amplituhedron actually convex according to this previous notion of extendable convexity? Well, so in general, one containment, you have to look at the intersection of the Grassmannian with the polytope, and you have to check that this intersection precisely gives you the amplituhedron. So in general, for all parameters, one containment follows immediately. So this follows by commutativity of this diagram, basically. By commutativity of this diagram, one containment is always true. And the fact that the amplituhedron is extendably convex now is equivalent to saying that this containment is an actual equality. So you need to check the reverse containment. If the reverse containment holds, then the amplituhedron is going to be convex. So here are a couple of examples and non-examples. So for m equals 0, well, this is a bit of a dummy example. Everything is just a point. And in this case, it is extendable convex. All the notions collide. For m equals 1, the amplituhedron was studied by Karp and Williams, 17, and they showed that the m equals 1 amplituhedron is a union of the bounded chambers of a cyclic hyperplane arrangements. So here you have in green an amplituhedron is a union of 3, 5, 6 bounded chambers of this cyclic hyperplane arrangement. But on the other hand, this is the example we had previously for the exterior cyclic polytope. The exterior cyclic polytope is is definitely bigger because the amplitude in this picture is not convex. So remember that in this case, our Grassmannian is nothing else than P2 or P2 star. So the notion of convexity is actually the convexity you would think it is in this plane. And you can see that this polytope is strictly bigger. So this containment is strict in this case, and this is a general fact for m equals 1. So the m equals 1 amplitude is not extendably convex. And in general, there is this philosophy that for m odd, amplituhedra are bad, and for m even, they are nicer. And I guess this is another example of this phenomenon. And what we did is to show that for m equals 2 and k equals 2, so kind of a specific set of parameters, but of physical relevance. So because they're relevant for some actual amplitude in physics. For this specific set of parameters, the amplituhedron is extendably convex. So we could prove the reverse inclusion. And this was somehow the proof is so here I outlined a bit. The idea is topological in spirit. So to prove the reverse inclusion, there are some things you would like to check. At least this is how we proceeded. So you want to check that the intersection of the Grassmannian, in this case, is GR24. So GR24 intersected with the exterior cyclic polytope is a regular semialgebraic set. So regular is a bit of a technical property. It means that the semialgebraic set is contained in the closure of its interior. So it somehow has not lower dimensional pieces hanging around. So this is one thing that we have to check. The other thing is that this intersection is connected. And the third ingredient that we used from the literature, actually from a result of Van der Steen and Tellen last year, is a containment of the algebraic boundary. So, but you see these first two steps are really topological in spirit, and I think is an open question and interesting direction to go if there is a more combinatorial proof of the convexity of amplitude. And by more combinatorial, I mean to show the reverse inclusion by checking inequalities, for example. So the amplituhedron, at least for m equals 2 and all k actually, has a nice understood description in terms of inequalities of some Plücker coordinates. And maybe one can cook up more inspiring or more inspired proof of this result, which we believe to be true. So we believe that amplitude is extendably convex for m equals 2 and all k's, but we could not prove it. So how we compute the exterior cyclic polytope? So here's a way. So this computation is described for k equals m equals 2. So C2, and I'm taking here n equals 6. So what we are having here is a 4 by 6 matrix. And a way in which I can cook positive matrices is by taking 6 points on the moment curve. So you see each one of these columns represents a point on the moment curve. And in order to have this matrix positive, I take an ordering on the values, an increasing ordering on the values. So these are consecutive points on the moment curve. Then to look at the k equals 2 exterior cyclic polytope, I have to look at the wedge 2 of z. So this is in the linear algebra sense is a linear map. Is a linear map between R to the 15 and R6. And so it's a 6 by 15 matrix, and its entries can be computed by wedging together the columns of Z. So in this way you build, so remember that the columns of this wedge 2Z now represent the vertices of our exterior cyclic polytope. So C226 is the convex hull of these 15 points. in P5. And then one can compute, for example, the F vector. So here's the F vector of this guy. It has well, it has 15 vertices as an input basically, and then it has 30 facets, for example. And here are some details about uh, what happens at the facets. We have 15 four simplices, double pyramids over pentagons. We have some cyclic polytopes, four-dimensional cyclic polytopes, and then we have some extra facets. So you can study these polytopes computationally by parameterizing the z's. And there is a nice graphical way of representing the facet hyperplanes when k equals 2. So the idea is the following. So each facet hyperplane contains a certain subset of vertices, and each vertex now correspond to a second exterior power of columns of z, so some zi wedge zj. And I can really think of these ij as being edges of a graph, on n vertices, where this n is really the parameter in the exterior cyclic polytope. So now I can identify each facet hyperplane with the graph on n vertices. And here are the graphs for corresponding to facets for C226. So here is some extra details about this example. So you build this wedge to Z matrix. This has 15 to 6 maximal minors. And then, well, you can study, you could study, for example, the matroid or the oriented matroid associated to this wedge to Z matrix. We investigated a bit that, but I think it's an interesting direction to go, to study more the combinatorics of this of exterior powers of oriented matrices. Anyway, here are some numbers. Here are the graphs. The graphs associated to the non-vanishing minors of wedge 2 of Z for this case. And in particular, we find that the oriented matrix is almost fixed. So the sign of all the maximal minors is fixed once you order the points on the moment curve for sampling Z, except for a special one, which is this minor here, where you take the wedge 2 of consecutive points on the moment curve. It is somewhat a special polynomial that was quite surprising. A very nice observation of Lizzie. So, right, in general, the combinatorics of these polytopes depends on Z. So I did not give you an explicit example, but uh, this is quite easy to check in the sense that you start computing these F vectors. You can see that once you vary these A, B, C, D, F, these facets may vary. For example, these three facets change once you change the values of A, B, C, D, E, F. So one thing is that the combinatorics of the polytope depends on Z, even on Z being a positive matrix. On the other hand, the combinatorial type is constant for positive Z, at least generically, outside of precisely this polynomial that we saw before. So this is actually the fully encodes the locus where this combinatorial type of the cyclic polytopes for m equals k equals 2 degenerates. It's just by this determinant, which in Plücker coordinates looks like this. So these are Plücker coordinates on the on six on the 4 by 6 matrix Z. So this is cutting out a locus in this positive matrices here. And this, by the way, a cluster coordinates on GR4 n. Sorry, a cluster variable of GR4n. So it's quite intriguing. It would be nice, I think, to understand more generally for other MNKs how the combinatorial type of this exterior polytope changes if one can prove that generically it's fixed and to determine in which loci it degenerates. And if they are always, for example, if these are loci are always encoded by cluster coordinates, cluster variables. So here is another computational table. We provided some F vectors of this exterior cyclic polytope for m equals k equals 2 and increasing n. Now, I told you that Hodges had, going a bit back to the history of the amplitude, and Hodges had this very nice observation that amplitudes could be encoded as volumes of polytopes. So this was the motivation for our project, is to extend this picture for other amplituhedra that are not necessarily polytopes. So this was basically the observation by Hodges. What about higher k, where an amplitude is not just a cyclic polytope? So now that we understood a potential notion of convexity, we turn to the notion of duality for semialgebraic sets in projective varieties. So here I guess I recall the definition of polar dual of a semialgebraic set. So this is for a semialgebraic set in Rn, and here are some examples. We define the polar dual by all the vectors whose a scalar product is at least or is greater or equal than -1 for every point in S. So I fix a scalar product in Rn. For us, it won't be a problem. We have because we want to think in the end we are very much tied to this non-negative Grassmannian. We are gonna take the standard basis and consider a standard scalar product. This is what we're gonna fix. So you need to fix a scalar product to define this. And here are some pictures. So for example, here you have this pink semialgebraic set by the polar duality is mapped to this light green. So it's bounded by a conic. Here is the dual conic. And for polytopes, remember that the convex duality or this polar dual reverses the F vector. So here, for example, I have this bipyramid is mapped to the cube. So in the very same naive way in which we define convexity, we can define duality. So for a semi-algebraic set, again in a real projective variety X, we define the extendable dual by first taking the convex dual in the ambient projective space and then intersecting back with X. And this is the same really as taking the convex hull, then dualizing, and then intersecting with X, where this duality is really happening in the ambient projective space. And as before, you can fix an affine chart and do everything in an affine chart, as long as this affine chart contains fully your semi-algebraic set. So a very nice example is that of the non-negative Grassmannian. So this was always our test example, that it should behave as the simplex. So it was okay for convexity and it's okay for duality, because again the non-negative Grassmannian is by definition the intersection of the Grassmannian with the non-negative simplex. And if you dualize the simplex in the ambient projective space, it's again a simplex. And this is really saying that the non-negative Grassmannian is self-dual according to this notion. Now, in order to study duality of amplituhedra, we were led to considering a deformation, or related object to the exterior cyclic polytope, which we call the Schubert exterior cyclic polytope. And this is a bigger polytope where you start from the exterior cyclic polytope and you delete all the facet hyperplanes that are not defining Schubert divisors in the Grassmannian. So certain hyperplanes. So each hyperplane is dual to a point in the dual projective space, and this point may or may not live on the dual Grassmannian. If it does, we call this hyperplane Schubert, and then we are keeping those facets. If it does not lie on the Grassmannian, we are discarding those hyperplanes. So this is a bigger polytope, but it has somewhat a nicer combinatorics. For example, we could understand fully all the facets. For m equals k equals 2, the facets of this Schubert exterior cyclic polytope, or equivalently, the Schubert facets of the exterior cyclic polytope, are n choose 2 and are dual to these points that can be written out explicitly. So this means considering so there's a bit of a physics notation, I guess. This represents a plane in P3 spanned by these 3 points. And if I intersect these two planes, I have a line in P3. And this line in P3 is really a point in GR24. So the Schubert hyperplanes for k equals m equals 2 are all dual to this kind of lines in P3, given by the intersection of these two planes. And going back to the example of the exterior cyclic polytope for m equals k equals 2 and n equals 6. So this was the graphical representation of all the facets. And among these four types, these are, by the way, up to symmetries. So among these four types of facets, three of them are Schubert. And in particular, the first three. So the first one is cutting out a set in the Grassmannian, which involves all lines in P3 meeting 1, 2. And similarly, this kind of interpolation conditions characterize also these other Schubert facets. And in this case, we have 15 of them, 6 choose 2. So the exterior, the Schubert exterior cyclic polytope in this case will be defined just by keeping these facets, these 15 facets out of 30. And these Schubert exterior cyclic polytopes can be understood in terms of a map that is familiar to cluster algebra people. So this map was introduced by Marsh and Scott in 2013. It's called the twist map. And it's a geometric construction and goes as follows. So we have these, the columns of Z, we can regard them as points in R to the K plus M. And so if we wedge enough, many of them, then we can identify this wedge product as, again, a vector in our K plus M. In principle, in our K plus M dual, but we can identify, again, this as a vector in our K plus M. And I'm going to call this Wi. So we can look maybe right away at an example. So if I take a 4x6 matrix here, Z1 through Z6, this Wi, for example, W1 would be the wedge of 3, 4 vectors. And this I can identify with 4 vector itself. So if I extend now, if I use this construction to define a map between matrices. So I can take a K plus M comma N matrix and map it again to a K plus M comma N matrix where I put in the columns these Wi's. Then what Marsh and Scott showed is that this map preserves positivity of the maximal minors. So the image of a positive positive matrix is again a positive matrix. And in this example below, this would you would map a 4 by 6 matrix to another 4 by 6 matrix, where each Wi is given by this triple wedge. So how does this map relate now to our story? And this was quite surprising, and it's related really to convex duality of this polytope. And the statement is the following: that if you take the Schubert exterior cyclic polytope for k equals m equals 2, and that this is really equal to the convex dual of the exterior cyclic polytope, but built out of this W matrix now. So somehow, if you think of this duality operation, it intertwines with this twist map. And by the way, I didn't write it out here, but this twist map, at least for k equals m equals 2, is an involution as the duality is. So you can also rephrase this as saying that the dual of the Schubert exterior cyclic polytope is the same as the exterior cyclic polytope with a twisted matrix. And we believe that this is true for m equals 2 and all k, but we don't have a proof of this. But this was really the key result to understand what duality does according to this notion I introduced before, what duality does to the amplituhedron. Basically, directly from this result, we can deduce that the extendable dual of this amplituhedron for k equals m equals 2 is again an amplituhedron, but for a twisted matrix. And this twist is very nice. It has also a physical meaning, and it's related to reversing the orientation of space-time somehow. It's a curious. It's curious that this very geometric operation has also some physical meaning actually. Okay, I want to conclude by mentioning some open problems. So I told you that it would be interesting to look more generally at the combinatorics of this exterior cyclic polytope. I think it should be true that at least for generic Z, the F vector is constant, and then it would be even more interesting to determine the loci instead where it may degenerate, and to characterize them. And then, of course, is the extension of this duality in relation to the twist map, if it holds for other parameters. So we studied always this very specific case of k equals m equals 2, which coincidentally is of interest in physics. But I told you also at the beginning that the actual parameter we're interested in is m equals 4, which of course leaves it becomes higher dimensional and everything becomes more complicated, but it would be very interesting to make similar statements for m equals 4. But I really see these first two problems as potentially purely combinatorial, while for the third problem, checking extendable convexity for other k's and m equals 2 or for m equals 4, I don't know if one can find a different, more combinatorial proof. Then it would be interesting by passing these topological arguments we had. And then, yes, maybe this is also interesting, like the relation between the triangulations of the exterior cyclic polytopes and tilings of the amplituhedron. So there is a very, very nice and rich combinatorics of the amplituhedron. in terms of its tiles. Um, and is very well understood, for example, for m equals 2 and all case. It would be interesting to study the triangulations also on the side of the stereocyclic polytope and see how they behave with respect to the tiles. For example, are the tiles themselves extendable convex? What are the polytopes associated to them? And then the last one is uh, more towards positive geometry. So maybe I won't comment on that. Mm, right, and this is okay. This is a bit of a more this is an advertisement slide in terms of this original question of expressing amplitudes as dual volumes. Well, with Lizzie, we really try to answer to the question what should be the dual semialgebraic set, but we believe that there is an extra ingredient to this whole story and is a bit more analytical in spirit. And it has to do with finding a probability measure supported on this semi-algebraic set to close this picture. And with Prashant, we looked at this in a companion paper. Um, okay, thank you. I think this was what I wanted to say.
Thank you very much, Elia. Are there any questions? I would have maybe two related questions. So first, could you just clarify what you mean by combinatorial type when you discuss how it's constant for the exterior cyclic polytope?
Yeah, I really think the F vector.
Okay.
Yeah.
And then a follow-up question would be, um, so these cluster variables which cut out the locus where combinatorial type begins to vary. I'm wondering if there's some kind of correspondence between these cluster variables and maybe the cluster variables that can or can't appear in the expression for the symbol in the like cluster alphabet, or is anything known about that?
Very nice. Very nice question. Yes, yeah. So there is this conjecture indeed that all, at least all rational letters that appear in the symbol are cluster variables. And indeed, if you look at this polynomial in the Plückers, it is a singularity of an amplitude in unequal four super Mills, but I don't think it's clear why it appears here in this context.
Mm.
I don't think it's really clear. It's surprising. I think it's surprising that this locus is cut out by a cluster variable to me,
Mhm.
but I don't see the relation of currently of this geometric meaning of this polynomial with this other meaning as a singularity of um, of the amplitude. Because if you think, even if you think of the fact that the amplituhedron defines somehow the amplitude, the combinatorial type of the amplituhedron turns out to stay fixed for varying z in the space of positive matrices. So this is really a statement about this exterior cyclic polytope, which the amplituhedron doesn't really see. So it's
Mhm.
surprising that this polynomial appears in that other context, which in
Mhm.
principle you would expect to be blind to the exterior cyclic polytope.
Yeah. Okay.
But yeah.
Interesting. Thank you.
Yeah, I have another question. Sort of from the beginning,
Mhm.
can there be made any connection between the Feynman diagrams and the amplituhedron?
Hmm. Yeah, yeah, this is interesting. And I think so these positive geometries were born, I think, with the amplituhedron. So the amplitude was the first example, but then since then people found positive geometries in other quantum field theories. So there is an amplitude for a different theory of scalar particles, where actually and the geometric object there is an associahedron, so it's actually a polytope. And in that case, well, the associahedron really encodes the combinatorics of triangulations of polygons. And the same combinatorics is captured by the Feynman diagrams in that theory. And this is precisely why that geometry arises in that context. So in that case, I think it's really clear. It's how the geometry emerges the connection between Feynman diagrams and in that case the vertices of the association. But in the case of unequal force supermagnets, I think it is mysterious. It is mysterious because now we are talking actually about the scattering of gluons. So there is extra structure to these particles, which is this K, the helicity. So these graphs actually that I drew here, there are 220 because so if you would count these three symmetry classes of graphs, even if you label them by 1 to 6, you would not count 220 because secretly I omitted some extra labels associated to this K. So what I'm saying is that these particles now have some extra degrees of freedom, and I think it's not clear how is that connected to the geometry directly, or at least combinatorially. I would say it's not clear. Like,
Oh, thank you. I have another quick question. Towards the end, you mentioned a tiling. In that context, what would the tiles be?
yeah, a tile for the amplituhedron is defined. So the amplituhedron, I gave the definition is here. So is the image of the non-negative Grassmannian. And the non-negative Grassmannian has a very nice structure in terms of positroid cells. So you could ask which positroid cells map, for example, injectively, injectively in the interior that have, for example, degree 1 on the boundary, and then this is basically would be, I think, the definition of a tile. So I think the images well-behaved images of positroid cells from the negative Grassmannian. These are the tiles for Amplituhedra. Which for exterior cyclic polytope would be nothing else than the triangulations coming from injective images of boundaries of the simplex upstairs.
So it's not at all like the tile another context, like the tiling of a set of squares by dominoes.
I don't think so.
Where you have two cells, you sort of where you exactly cover a collection of cells by certain combinations of cells. Yeah. Okay, thanks.
Yeah, I see Yannick has a...
Yes, thank you. I have a very naive question. Can you go to page 21?
Yep.
Yes, so I see this identity as follows. So on the left-hand side, you have a physical object. On the right-hand side, you have the volume of a geometrical object. If you replace amplituhedron by associahedron, permutohedron, cyclohedron, I mean, you have a whole collection, a zoo of combinatorial polytopes related to the amplituhedron, of course. Is there any left-hand side on the pictures? So does it make sense to talk about some amplitude related to permutohedron, some amplitude related to more general polytopes?
Definitely. Well, I think the best person to answer this question would be Thomas Lamb. He has definitely a paper on how even to associate amplitudes to matroids, I guess, even more generally.
Oh, okay.
So definitely. Then the true question is, what is the physics behind that? If there is any actual physical theory that has that amplitude, and that is well, it is really a big question, and I think we're investigating. So these positive geometries, they are popping out slowly in many places in physics, from cosmology to supersymmetric theories to non-supersymmetric theories. But there is no standard procedure to get them. It's a mysterious hunt.
Yeah, it's quite mysterious indeed. Thank you very much.
Thank you.
Elia, is it known? So for the cosmohedron, like cosmohedra are related to wave functions, is this kind of like identity known in that case? Or is
Um,
this like
yeah, the cosmohedron, unfortunately, is slightly weird. It captures a lot of combinatorics, but there is not the quality relating in that case the the wave function of the universe, what
Mhm.
would correspond to the amplitude, is not directly related to the canonical form of this polytope. There is some extra mechanism to get out of the canonical form, the amplitude, and therefore this equality does not hold in the sense you would expect it to be. So you cannot take the dual of this cosmohedron and expect it to give the amplitude. But it would be interesting to go to see what the duality means in this construction that Niemann collaborators have. I
Mhm.
mean, this dual picture was played a very nice role in the case of the associahedron. So it has some physical meaning. This duality is related to string theory in some sense. So I think whenever possible, it's nice to explore it. It's just the cosmohedron has a bit of a gap in the level of this equality.
Mhm. Okay.
But maybe that's a feature.
Any other questions for Leah? Okay, if not, let's thank him one more time.
Thanks a lot. Thanks a lot.